So let's start. Good morning, everybody. I hope that you are doing well. And welcome to the week 9 of AIRCAC. Last week, in week 8, we extended our smart campus simulation into multi-model research problem. We combined sensor synthetic thermal images, HVAC, audio, and maintenance text. We first tested each modality independently, and then we tested the early fusion and late fusion. And if you remember our main finding, adding more modalities did not automatically improve the prediction. The sensor modality was already the strongest, and fusion essentially did not beat it. And at the end of the week 8, we said that that this creates a new question. The sensor model gave us a very good sensor, but can we actually trust that score? That is exactly what we are doing today. So today we move from simply obtaining a good predictive results to asking whether that result is scientifically defensible. So a model can give us an impressive number for many wrong reasons. Maybe the model accidentally saw part of the answer. Maybe the training and testing data were improperly mixed. So maybe also we selected the metrics that makes the model looks better than it really is, or maybe the ranking is good, but the predicted probabilities are not reliable. Or perhaps the average performance looks good while the model performs poorly for one particular group. So today, the objective is not simply, can we create a high score? The question is, can we produce a score that we can defend? So we continue with the same smart campus problem to follow the strategy. Our target is very specific. We are not asking whether CO2 is already high and remain high. We are asking whether the new high CO2 even will begin during the next hour. We have 14,380 early prediction samples. So we, rather than taking the minute, we take the early. So it's just to reduce a little bit the number of samples, because we have more samples in minute, and we can have more samples in second, but it's useless to have all of them. It doesn't, it's not useless, but it doesn't provide a good it will not help us in physical way. So we cannot we cannot switch and on the ventilators in 1 second or in 1 minute. It will also it will harm or break the motors. So only about 80% of the samples are positive. This is a rare events prediction problem, and today we deliberately use only 9 leak-free sensor features. Every remains synthetic. These are synthetic. These are not real CSU built-in measurement. So it's always, we need to remember that it's not realistic. So to avoid maybe the one that you will see this week, and he doesn't see the previous weeks. Maybe he thinks that it's real measurement, but it's not. It's only synthetic. We generated using our digital twin. The first issue we need to discuss is probably the most dangerous one, data leakage. Leakage means that during training, we give the model information that would not actually be available when making the real prediction. There are two main types here. The first is feature leakage. One of our variable contains information about the answer of the future. The second is split leakage. Related observations appear in both training and testing. The problem is that leakage does not usually cause Python to fail. The model runs perfectly. It may even produce excellent score, but the score is invalid. Here we make the leakage complete. On the left, we have examples on forbidden information. For example, the current hidden true CO2 value next hour occupancy or privileged information from the simulation. We deliberately create these variables only so we can measure the how badly they inflate the results, but they are never allowed to in our honest models. On the right side, we have the split problem. So if we randomly shuffle the time series data, our T may appear in training while our T plus one from the same zone appears in testing. Those samples are highly related. So our solution is simple. Respect time and do not randomly shuffle these experiments. So now we build the feature set correctly. Even variable must represent information that would genuinely be available at the prediction time. For example, recent observed CO2 is recent trend, current ventilation, temperature, humidity, outdoor PM 2.5, filter efficiency, and recent energy use. Notice that it is missing. There is no hidden latent truth. There are no future measurement. There are no privilege schedule information. The truth is very simple. If we would not know it when making the prediction, it cannot be a feature. So the same principle applies to how we split the data. The earliest day are used for training, the middle period is used for validation, and the last days are kept the final test. We never randomly shuffle across time. The validation set is also where we feed the calibration. The test set remains untouched until the end. So the test is not something we repeatedly use while modifying the model. It is our final independent check. So this is how we need to check and to avoid to provide the correct results or metrics results. And if we have good results, so we means that the model is how to say generalized. So now we arrive to another important issue, because only about 5% of our samples are positive. Some metrics can make the model looks much stronger than the really is. Look, for example, the rock AUC. It's approximately 0.902. At the first glance, that sounds excellent. But now look at the PR AUC, it's only approximately 0.244. That tells us much more realistic, strong about predicting this rare event. So the first problem, I would not headline the rock OC alone. The more honest headline is the precision recall RUC, AUC. Together with its uncertainty. We also calculate the barrier score and the calibration error because we cannot only we care not only about the ranking but also about the quantity of the probabilities of themselves. So this is very important. So the model may rank events correctly while still giving poor probabilities. For example, if the model says 80% risk, we want that number to have some statistical meaning. This is what calibration examines. We use the reliability diagram and expected calibration error. Then we apply isotomic recalibration using the validation set only. Here, the ECE improves the approximately from 0.45 to 0.11. So when it decreases, it's much better because it's error. It's the error. I would say when it's near to zero, it's much better. The ranking does not change in this case. We are improving the quality of the probability estimates. So whenever the decision depends on the predicted probabilities itself, calibration matters and matters very, very much. So another important point is that we should not report only one number. The metric calculated on one test set contains sampling validity. So we use bootstrap resampling to estimate an interval. Our ROC AUC is approximately 0.902 with an interval from about 0.884 to 0.9188. Our PR AUC is approximately 0.24 with an interval about from about 0.201 to 0.308. So notice that PR AUC interval is relatively wide. That itself is an information. It tells us that performance on these rare events has meaningful uncertainties. So these are statistical intervals, not guarantees about future real-world performance. So a signal average can also hide where the model is weak. So we break the test results down by building and by time of day. Building one for performance best at approximately 0.941 AUC. Building 4 is weaker and approximately is 0.871. And 9 time is the weakest period at approximately 0.810. Why does this matter? Because if we report only the overall average, we may miss exactly where the system is most likely to fail. So responsible evaluation should not ask only how good how good is the model overall. It should also ask where does the model fails. This is also very important. Now we collect all the information into one document, and we call it the model card. The model card records the intended use, the data set, the train, the validation test split, the metrics with intervals, calibration results, subgroup performance, and limitations. And importantly, this guaranteed from the executed results file. So the model card is essentially the scientific paper trail of the model. Someone should be able to read and understand not only what the model does, but also what it does not support. And also, this is very important. So now let's move to the practical part. Our demonstration is the leakage audit. We will build the prediction data set, deliberately compare the honest and leaked configuration, and then train and final leak-free model. The objective is not just to say that the leakage is bad. We are going to measure exactly how much it changes the results. So going from how the leakage is to what are the measures that we are doing exactly. So we ran the model, and now let's see what's happening when we allow leakage. With the honest features and temporal split, the PRC is approximately 0.4. 244. But when we introduce the forbidden information and the improper split, PR AOC can raise to approximately 0.969. Think about that difference. The underlying scientific problem did not suddenly become easier. The model did not suddenly become revolutionary. We simply allowed it to see information that it should not have. So leakage transforms a modest rare event model into what appears to be an almost perfect model. So all this results I will share later on the papers that I worked before, because as I said, I only applied what I had before, what I worked before a long time ago, about how to say this to get these results. But for the mathematical and the background, I will share. You will find the codes. You will find the codes in my GitHub, and also I will share the what I should say the papers that related to either the archive papers or the published papers later on. So why this extremely high metrics should sometimes make us ask more questions, not fewer. So because the variation is from 0.2 to 4 to it's huge. It's almost more than three times improvement. And it's this one, it will ask us how to say, make us to ask more questions, not less questions. And this is very, very important. Once we remove the leakage and evaluate properly, this is the performance we report. The ROC AUC is around 0.902. The ROC is the PR AUC is around 0.244. Barrier score is approximately 0.343, and the EC E is approximately 0.23 in this evaluation. The important point is not that these numbers are spectacular. The important point is that they come from the honest held out evaluation. This is the results that we can defend. So next we perform the calibration, and the closer we are to the diagonal, the better the predicted probabilities correspond to the observed frequencies. After isotonic recalibration, our ECE improves from approximately from 0.45 to 0.11. And remember that the calibration mapping is fitted using the validation set, not the tested set. So again, we protect the independence from the final test evaluation. Now we attach uncertainty and headline matrix. We ran 2,000 bootstrap resample samples of the test set. Instead of saying only PR AUC is 0.244, we say POC is approximately 0.244 with 95 percent bootstrap interval from 0.201 to 0.308. This is also, we need always to give margin. It's not only fixed there. That give the reader much more information than a single point estimates. And again, these are statistical intervals on this synthetic test dataset, not guarantee about the real world development. So if you want to apply that in the real development, we need to don't how to say make the synthetic data as realistic and how to say the base as synthetic and apply it in realistic data how to say scenarios without more studies and more how to say we need to do it otherwise. Not only that, it's not only take and run. So finally, we examine the subgroups. The performance is not uniform. As you can see, building 1 is strongest and building 4 is the weakest and weaker. And how to say nighttime is the weakest condition with AUC of approximately 0.810. So here how to say we need this tell us where additional data is needed, model improvement, and whether the investigation may be needed. Good average does not mean every subgroup is actually tell us equally well deserved. So we need also the time of the day is important, and as we can see, the morning and the afternoon are the similar, but the night is less, and also B2 and B3 are similar, but compared to B1 is the best and the worst. But we cannot say the worst and the best. We are. This give us less generalization. So either the data set that we used for building building 1 are more how to say the model reacts to the building 1 more, or reacted less for building 4. So it's not how to say, it's not maybe we can use another data set and we can find that the nighttime is better. Why? Because here the night time we will not find a lot of people. So this is also another parameters that we need to introduce. If we don't have a lot of people, so you don't have a little you don't have much CO2. So these data sets, or this how to say distinction, or this information also how to say provide us Another constraints of the models that we need to take care about it and make everything I would say if we want to study the realistic model, we need to take everything into account, and then we introduce I would say the model, and we introduce the improvement that we want to do. So when we say responsible reporting, so these are three commitments I want to remember. I want you to remember, or all of us we need to remember. First, report the honest numbers, not the leaked numbers. The second, use the metrics that match the research problem. For rare events like this, PR AUC with uncertainty is more informative than simply reporting accuracy of ROC. ROC. This is also how to say very important, because sometimes we can use some metrics, but these metrics give us good results. Why we are using other metrics? Just to It's not just to use the other metrics and to show that we are using a lot of metrics. No, it's the idea is we need to use metrics that help us to understand better the problem and to provide honest results, because it's case. For example, let me for example give another example. If we are using only the prediction in time and how to say to have the accuracy, RMSE is the best, but it gives us the how to say metrics. But if we want the quality is we need to use how to say coefficient of covariance, or coefficient of correlation, and so on. So this is the choice, or the choice of the metrics that we are using is not randomly choose the metrics. We need to choose the metrics that they help us to understand and I would say to provide results results that satisfy the research itself, the research problem itself, or the support the research problem itself. And the third point, document the limitation, calibrations, subgroup features, assumption, and limitation should be a part of the result, not information that we hide or we at the end. No, it's the limitation help everybody, help how to say the reviewer to understand, help the reader to understand, help you to how to say to have this work be continued. So if you don't say the limitation in the future work, you will how to say people why they will how to say what's the problems that you will face if you will how to say use your model in the future. This give you how to say people they will use your model as base, and they will improve it based also your notes. So it's not how to say limitation. We should do the limitations. No, we should how to say the limitation part is to my opinion is the most important part of the paper, because it shows because you are the expert in this field and you write this paper and you are saying this is based on my expertise, based on my research, based on my finding. I find these limitations and I propose the following future work. Either you will work on them or another one will work on them, and this is how it works in research. So for your own research and exercise, I think it's good if you can build a small prediction study that you could defend to the reviewer. We need to create leak-free features, use proper train validation test split, report appropriate metrics, check the calibration, and attach uncertainty intervals, analyze the subgroups, and finish with the model card describing what the model can and what and cannot support. The objective is not to minimize the score. The objective is to produce evidence you can defend. So it's clear that how to say that this can help. It's not only can help us not only to how to say to for our actual research, but it can help us in the future because it will help us to defend well the problem. And as I said at the beginning, is not the goal of this is not to focus on only one research. You can apply these models and these metrics and this what we are finding here, what we are describing or learning here is only to help you how to start using your own research, using your how to use AI to help you accelerate your research and improve your how to say and to go easily to your target. This is what I want to say. Sorry. So so we can summarize today's week today's how to say uh, uh, what we can say today's week by saying the following if and also we need to predict how to say to have prevision that what we will do in the next week. So as a recap, in week 8 we found that CINSER's modality was our strongest prediction signal. Today in week 9 we asked to whether the strongest results could actually be trusted. We controlled the future leakage and split leakage. We selected the metrics appropriate for rare event problem. We calibrated the probabilities and we quantified the uncertainty, and we examined the where the model performs poorly. So now we have something much stronger than simply a good score. We have a validated model with documented limitation, and at the end of this week, we planned the next step in week 10. I don't know, in week 10 we can put it to week 10 and 11 later on, but now let's focus on 11 because we need to finish this how to say this training by the end of August. As planned before, maybe we can put 1 hour in the how to say the consultation time, or I will put the next Friday for 2 hours, 2 hours other than 1 hour. But I will discuss with the responsibles to how to do that. In week 10, we are going to take this validated model and place it in behind an interactive digital twin dashboard, so that a researcher or non-programming can explore scenarios, change conditions, and inspect prediction without directly running the Python script. This is my goal for the next how to say next week. I hope that I will finish it by the next week. If I don't finish it, I will only introduce the how to say the first, and then we will continue together. But so our progress continue from 6 weeks. Just to remember that from week 7 we build the simulated world. In week 8, we make it multimodal. In week 9, we validate the predictive evidence. And in week 10, we'll turn it to evidence. We'll turn that evidence into an attractive research tool that I hope that it will be released by the end of these sessions. And if I would say, because we have time, I can go back to slide 8. Just I want to explain something here. So before we how to say we finish, we can how to say have something to say about the my research. I would say sometimes we see a paper saying, for example, our model achieved not 90% accuracy, or our RC achieves is above 0.5, and immediately we think that the model is excellent. So, but the first question should actually be, what is the distribution of the problem? It is only, how to say, around 5% of our samples represent the onset event. That is completely changed the how we should interpret the performance. Imagine a much simpler example. Suppose I have 100 observations. Just I want to explain something here very important because we have time. Suppose that I have 100 observation and only 5% of that I care about. A model can be approximately good and recognizing the 95 common cases and still be very poor at recognizing those 5 important events. This is why the choice of the matrix is not something that we do after training the model. It is actually the part of the research design. In our experiment, our ROC AUC is around 0.902. If only we put that number in the paper, it looks that extremely strong. But if we added now PR AUC, it is 0.244. Now we have different picture. The model clearly contains predictive information, but because the prediction recalls performance is above the rare event prevalence, but it is certainly not near perfect predictor. And this is something that I want to remember for your own research. A metric should reflect the scientific question, not simply make the model looks good. I can repeat it. A metric should reflect the scientific question, not simply make the model looks good. If I am doing medical diagnostics, fraud detection, equipment features, rare ecological events, cybersecurity attacks, or any other rare event problem. So the minority class may actually be the class that I care about the most. It's not the general cases that we can have everywhere. So what should I ask? What does the model do on that event? What is the precision? What is the recall? What is the precision recall behavior? and what uncertainty do I have around that results. This much more important than simply saying my accuracy is 95% or something like that. And this is also where AI tools such as Copilot or ChatGPT must be used carefully. They can calculate every metrics for us very quickly, but they cannot decide which matrix is scientifically meaningful unless we understand the research problem. I hope this point is clear, and I think we have also time. I can go to 14. I want also to return to these figures because it's probably the most surprising results of today's session.
Could I ask a question before you go on to the next point?
Tell me, please.
So you said something, really critical, and you said that basically the AIs really couldn't, I guess, assess the scientific truth, I guess. They can do a calculation and present an answer with, but they can't, I guess, evaluate the scientific merit. Am I understanding it correctly, what you said?
Yes, exactly. Yes. I said how to say uh, AI tools such as GPT or Copilot or else
Mm-hmm.
must we need to use them carefully. This is what they can calculate every matrix for us very quickly. Means that we can provide them the CSV file, and they can provide the metrics that we want. For example, RMSE, MAP, any metrics that you want to cut very, very fast. But they cannot decide which metrics is scientifically meaningful unless we understand the research problem. Because here, why we are doing this? Because if we take only the matrix ROC, it's 90
Mm-hmm.
0.9 or something like that. And the other one,
Mm-hmm.
if we don't take it, means that we are how to say we are saying that our model is perfect, but or strong, very strong, but in reality is not. Why? Because we take only the general case that I can find in reality, and we are not taking the serious cases.
Oh, okay.
This is the
Okay.
idea. The idea is it's an important question, Professor Kim. So the idea is, let's say, for example, I am treating with cyber attack. For example, cyber attack,
Mm-hmm.
and I have 100 case. 95% are almost similar
Mm-hmm.
similar attacks, and five cases are very rare cases, and I apply my model, and they say that it will, because I use a lot of similar data, the model will provide good results. And in reality, I need to provide a model that it can defend the five cases that the people they are attacking me in reality, because
Mm-hmm.
I can provide the results, but the model is useless in reality. You got the point.
Mm-hmm.
This is very important. This is how to say. Thanks, Professor Kim, for this question. This is the most important question that we don't how to say in the data itself. In the data itself doesn't mean that the model provide for this matrix provide good results. Means that this is the best model. Maybe other models that you are how to say comparing to are very very useful for the rare cases or rare events that we need to care a lot about them. So let's see, for example, I have 100 person that they are near to the bank. Five of them they are still in the bank, and I am saying that my camera sees 100%. I can see 95 person near to the bank. They are there, and I am okay. But in reality, I need to how to say to detect the 5% that they are still in the bank. This is the most important. If I take from outside my model is very very powerful, but in reality, it gives me I would say results that I don't need in real world. This is the idea.
Okay.
So here, just I want to add one thing for these figures, because I would say I need to talk about the PR and just to understand a little bit. Let's I would say what's happened exactly. PR equals 0.2244. When we allow the model to see information it should not have, it raises toward the 0.96. If I am very, I would say, I can read it. It's 9.69. So the model give us poor results if we give the, how to say, we gave him values, the most important values, it give us the worst results. But if you give them information, how to say, uh, the model that he saw before, it will provide us very high quality results. This that difference is enormous. It's not small results. So, but the reality is nothing meaningful happened scientifically. We do not invent a better algorithm. We did not collect better data. We did not discover a new scientific relationship. We simply allowed the model to cheat. This is we call it leakage. Is particularly dangerous than in AI research. And if we our code crashes, you know what something that something is wrong. If Python give us an exception, you investigate it. But the leakage is different. Everything looks good. The training completes. The figure looks beautiful, and the metrics may even became 0.99. And this is exactly why it can survive all the way into the manuscript. Let me give, for example, another way of thinking about it. Suppose I tell students that tomorrow I will give them an exam. Then during the training, I accidentally give them tomorrow's answer sheet. Then the next day, the score will be 100%. Can I conclude that my teaching methodology is excellent? Or of course, it's not, because there's something wrong here. That is essentially that future leakage does. The same idea applies to split leakage. Imagine that I show the model Monday's morning, Monday's afternoon, Tuesday morning, and Tuesday afternoon from the same high correlated system. Then I randomly put some of this observation into the training and some into testing. The test set may looks independent in computer because it has different row of numbers. But scientifically, however, the observation may be almost copies of the condition of the model already saw. So the question I recommend here is whenever you review an AI paper is how exactly was the train and split data created. Not simply did they have the test set, ask what is random, what is temporary, what is subject level, what is patient level, what is built-in device level and site level, and so on. So depending on the research question, the collect split can completely different. And this is why our experiments we made the leakage visible deliberately. I prefer, how to say, uh, if I can say like that, teaching leakage by something, the misleading results, rather than simply putting the bullets in avoid data leakage. So again, once we see here the PR OUC jump from 0.244 to 0.969, we understand why this is matters a lot. So one more thing, when we work in temporal time series or any temporal related videos or anything, the split is very, I would say, it's not dangerous, but it's it's important than the model itself. This is the first thing. So don't, I would say, shuffle or use the same shuffling model, shuffling data sets, and you say I shuffle the data set and I give the seed. It's not the issue for the seed or for the shuffling. The idea is we need to for example to keep some days, first days for training, second days for some days for training, for validation, and some days for testing, and it's not shuffling, so you can shuffle training itself, data set themselves, shuffle them to avoid also one another problem, overfitting is is very dangerous also in training. But don't shuffle it with the validation or with the testing. This is first. Second, the metric itself is very important, because based on the application itself, you need we need, how to say, to define the metrics, not to evaluate only the results, but to evaluate the model itself. The as we explained here, this is also very important. I think if this still time, we can, I would say, can also provide some for calibration. I could, for calibration, I talk here calibration. Calibration, not here. So also we need to always to put synthetic as it is, because going from the practical from simulation to the practical way or real world is not only plug and play model. You can find the model, but we need to modify the model to be, it's not adapted to work in real scenarios, because in real scenarios is not, even though we will do our best in simulation to reproduce or to twin the realistic model, but in all case you cannot, how to say, validate a twin, except you are using a realistic system or realistic data set. Then you can, when we move from twin to real, it will be, how to say, accurate. The idea is we need to how to say, talk about the model. We use first the data set that we are planning to use, and then we we we, how to say, train the model, have the results, and then apply which we call sim to real. So we apply the simulator here, but we can get the sensors from the reality. You get the sensors from reality and go give the actions to the reality. Only the model and the digital twin is here in the computer in that time, and if it works in that time, we can move, how to say, to the reality without coming back to the simulation. This is we have sim to sim, and we have sim to real, and we have real to sim. So we can provide the realistic models and bring it here to run the model. So I think now it's so just here to one word about the IUC achieved 0.9. The numbers appears as through there, we, how to say, were an absolute truth, but 0 point come from the finite test data set. If we collected another samples from same underlying system, would we obtain 0.902? Probably not. Maybe it would be 0.89 or maybe 0.991. This is very important. Maybe else another number. Why we should not think of metric is perfect fixed constant. Here we use bootstrap resampling. Conceptually is an idea is straightforward. How to say, we respectively resample observation from our test set, calculate the matrix again and again, and look at the resulting distribution. That gives us information about how much the estimated performance varies because of sampling. For the ROC UC, our interval is relatively narrow. For the PROC, is the interval is wider, as we can see in this figure. These intervals are not I would say provide us random. It's we calculated them using our data set. And this give us the margin that our errors vary. So where exactly we are is not only 1 point we can go until 0.2, and the reader, when he read like that, he will understand that this model can provide me 0.2, can provide me better results, but in median is not average. In median we have this point in the middle. So what we can see here, the uncertainty itself, it's a result. So don't, I would say, if I can say like that, take the uncertainty as an option or something similar. So take it as I would say a part of the result itself, and this is very very important. So. I think next week we'll continue, and I hope that I will finish the tool that I'm preparing for to help, because the goal is not to. At the beginning, I start only with Copilot and Python. Then when we work on something similar, I think if we can have I'll say dashboard that it will help people that they are not programmer, not I would say not they don't know Python or something like that. They can go and run the I would say this digital twin dashboard. I hope that it will be attractive, and I always updated it. Before it was how to say not how to say high quality, but I'm always updating it based on the time that I have. But my goal is to provide people a tool that it can help them later on to use or explore scenarios, change the condition, and inspect prediction without directly running the Python scripts or be I would say a programmer in the real way. So you can I know that everybody understands the codes, and there is no issue in the coding, but being a programmer, expert in programming, sometimes no need to be very very I would say programmer to understand things. So this is my goal, and this is the links always I give just to help people to maybe they are curious about the package that we are using. And always I need to remember how to say remind people that all the data are synthetic, the interval are statistical and not real world guarantees, no casual or development crimes. So this is very important. If we have some results, we can I would say you can find them in my published papers in the GitHub that I always update the new package that I am adding. And thank you very much for your attention. And if you have more questions, I'll be happy to reply. Else, I hope that I see you next week. And as I said, sorry, Dr. Professor Kim, just maybe I will discuss with Professor Ayesh and with you later. Maybe if I can finish, because this dashboard it needs a lot of time to explain. Maybe I will request to put it in 2 hours Friday, and also to finish I'd say this training sessions by the end of August. As planned before, but this one I will discuss with you in private later on with you and Professor Ayesh later on.
Oh, that's no problem. I had one quick question, then I'll let you go. How common is the data leakage problem when people are creating like these predictive models or these simulations? Is that a common problem? Is that it seems like it's a data handling problem.
No, no, it's a common problem. It's common problem. Like for example, why if even though GPT and Claude they say it can make mistake, it's not because
Mhm,
they have this they are doing that in purpose because they are AI. No, because the idea is it is learned and they give them huge data set, but they don't give him the whole data set that exists in the world.
mhm,
And also,
right.
if now I let me explain with an example. Maybe I can say. So let's, for example, you trained me to do something. You trained me to do something. You teach me the colors, for example, red, black, blue, and yellow. Just I'm saying. And now you gave me the gray. I don't know it. This gray. This gray, I don't know it before. I don't see it before. If I guess from where I should guess that it's gray, I will make it as how say the nearest colors that I know. It's black. I will say it's a black with white, with white. So this is how the models they are working. The data set it's continuous and it's the if I gave you the black and I give you the black minus 0.59, you cannot see it by your eyes, but in reality we have two colors here. So the white also and the red. Let me give you the red and the high red orange, high red orange, and you think that they are the same. So it's true. They are red and they are I already teach you about the red and the nearest red to it. So but if I give you how say different categories, you will not know this color. The idea is we need to the data set itself. It's more dangerous than the model, and this is
Oh, wow.
yeah, especially in time series. Or if I can now if I give you, for example, I'm saying now in Chicago, just I'm saying an example. In Chicago, all the winter is minus 11 degrees Celsius, or minus 13, or let's say in the winter, and they give you December, January as data set, and I told you predict February. It's 100% you will predict that February is also same. But if I give you January, December, January, and I give you predict August, here
Mhm.
it's not similar. You got the point? So don't give
Yes.
the model the similar data and say my model is good.
Okay. Wow. That was what you said was very profound, that the data was more dangerous than the model.
Yeah, because this is based on your expertise and you will define even though the matrix, to be honest, the matrix itself is more, it's not more dangerous, but it's make your eyes or your brain climb things that they don't exist.
Mhm,
If now I tell you that my results is I am using RMSE, but if I use another metric, it will not provide me the same high accuracy. It will provide me as we provide in the today's session that ROC it's very high, but PR it's small. So if I don't use, I hide PR and they show only ROC, you think that I think, oh,
mhm.
yes, provide the model is very, very high quality, but in reality it's not. It's not, because I take only the most, because ROC takes only the most probable values in the data set. So and the PR it takes the rare events that are more important than the general data sets. So this is we need to take care about not only this what the session of today. If we take as conclusion, we need to take care about the model. It's true that the model is very important, but the data and the metrics that we are using are also have the same importance as the model. This is the conclusion of this. If we take this as conclusion, it is the most important thing.
Wonderful. Well, thank you so much. This is so interesting. I've been enjoying this a lot. So thank you.
Thank you very much, and I hope to see you next week. Thank you very much.